Welcome back. The last part one got cut short, unfortunately, because of a few messages coming in. So now I've done a few notes here because we're dealing with a classical or some kind of classical-ish system. As we'll see, it's not really what I would fully call classical, although it's deterministic. If we write down the Riemann tensor in terms of, so this is GR, we've got the stress energy momentum tensor, we've got the cosmological constant term. Now, what we can do is, because we've got this field here, we're just talking about some decay, we're talking about exactly the symmetric case where we have a wave function and its reverse in time, and we can see very nicely that it's going to be real on t over 2, t equals t over 2, so we've got this nice zeta function like symmetry where it's real on that line, and so we can use all the nice reflection formulae to get the field strength over the whole of space, and in this case we're assuming that we're dealing with an infinite dimensional Hilbert space. Although it doesn't seem entirely important, we could be dealing with any Fourier transform really. But for the moment we can see that the cosmological constant, we really do kind of want that term to be zero, because that's the whole idea of this line, that the cosmological constant can be zero because we're getting an expansion and a contraction phase. So over the whole cycle, we're getting a space localizing to a point, localizing to a space, going to a global to a space, and then back to a point. So the total over the whole cycle, the cosmological constant is zero, and so we'd actually expect to be able to cross out this term, and but we do get at this point it's essentially lambda, the cosmological constant is positive, and in this place the cosmological constant is negative. And that of course gives, but over the average over the whole space is zero, and this is all because we've got positive and negative mode oscillators, and we can have positive energy conditions in both of these sectors. So essentially one of the sectors fills up the positive side of the spectrum, and another sector fills up the negative side of the spectrum, and so it's kind of essentially we're getting something a bit like a Dirac sea caused by the second interference of the second wave function. And the other thing is that all right, so now let's look at what's actually kind of going on from the propagation point of view. As we have these 2 points, and so let's imagine now that we extend this off in to infinity, then we get this kind of, if we imagine individual trajectories, or what we call geodesics, they're all going through focusing points, so they're kind of in the diagram, they're getting dissipated and then refocused. So the system is not dissipative like a propagator on its own. The free field theory is dissipative, but as soon as we get interactions, we get this the dissipation of the system cancels out because of these real lines or real surfaces, and So that means that if we scratch off this term, we just get the Riemann curvature in terms of a coupling constant and some function of the amplitude of this inner product. Well, the amplitude is the result of this inner product. And so this is some kind of energy from amplitude. Now, if we think about it, the energy density for things like boson fields or anything like that has a minus sign in it with the transpose. So if we think about having the stress energy momentum tensor, we've essentially got another kind of imaginary part which we can add to it to create a Hermitian tensor, and in this way this Hermitian tensor satisfies T star equals T, but it's in some high dimensional space depending on how many fields we have in this. So and there could be quite a few, all the gluon fields, all the electromagnetic fields, etc. And so they all have their field strength in this form. But now what we've got is a genuine energy density. So all we need is any function which basically just is going to take these terms to be probabilities and positive terms eventually, and so we we don't know that. We don't know altogether. There can be positive and negative energy flows within this space, but they kind of balance each other out. But so the point is that this Riemann tensor is uniquely defined by the wave function now. So and this function f. So there are essentially very few, if any, degrees of freedom, because we'll find probably that this f is fairly forced, because naturally, like the quark density function, for example, is going to be exactly of this expression. So all we want to do is find the stress energy momentum of these various wave functions, and that's all forced. That's all just, we don't have any real choice there. The equations seem to be forced by all the gauge symmetries and everything. So I don't think there's any choice, or it'd be interesting to see how much choice there is for this f, but I don't think there's much. And so the other point here is that because we're getting these focusing points, once we've gone past the point of focus, we can no longer talk about geodesics at all. So what is the status of a geodesic in here? Because this system has no back reaction at all. It's essentially a holographic equation. We give it a wave function, and then it generates a GUV, a bulk space for it. And obviously all the space and time, they're different, but here we got time running from minus infinity to plus infinity. And here it's going to be a distorted bulk time. But we've got the equations are exactly general relativity. And this is a puzzling problem, because surely general relativity does have quantum corrections, but this is saying that if you take account of the entire energy density that's assumed by this wave function in a product, then GUV is essentially forced. But things are not following particles that don't really exist. They don't really exist trajectories as such at all. So even though we might have a geodesic defined and a surface defined, and there might be a geodesic that passes through all of these points, because we've got this focusing going on, this this is not necessarily going to be a global solution anymore, and this is very clearly made by Ed Witten, that once you get focusing, you can throw away global geodesics. And so what this means is that geodesics only really work perfectly between interactions. And within that period, the it's essentially a free field. There are no interactions going on. So this is a peculiar kind of view, because it we lose a lot of the um, global properties of GR. There's probably still some approximate forms of them, but actually the exactness is only held at very short distances, and there nothing is following those geodesics, because we're actually getting a wave propagation rather than a particle propagation. So if we want, so this is peculiar, because it kind of is counterintuitive to the way that we think about GR normally as being a theory of geodesics, but here it's saying, well, yes-ish. And in fact, not really, because we keep on getting these interaction nodes and non-particle like propagation between those. So it's, what role do geodesics play anymore? It's difficult to say. Now, is there anything else from this? So we can imagine all of the content of the quantum side of the theory is in the imaginary part of a Hermitian tensor, and that essentially what we're doing here is mapping this Hermitian tensor IH onto the stress energy momentum tensor. So again, this is a derived process. So we go from a function, a phi, to a t, to a g, via an h here. So we can see, and one can pretty well draw these arrows backwards to imagine that if you start with any surface of these forms, that we can find a phi. You know, it'd be very interesting to see that way what holds true. What kind of surfaces do we need? What kind of orbifolds do we need to generate this the other way, the converse? But here very clearly we have a route from a wave function direct to the curvature tensor. Now, but this is all a bit odd, because what are we to make of effective field theory that corrects this, and what are we to make of the graviton? I mean, we could imagine that there are graviton fields in here, in the phi, in which case this becomes a very complicated geometric object. But again, for the moment, it's best not to, I think, focus on that and just look at the more elementary, in inverted commas, case when we're not dealing directly with gravity, and we're just looking at the gravitational effects of the matter fields, and without looking at any gravitational fields at all. Now, that one can imagine that, given that nature is as complicated as possible, that the existence of a graviton within will make very peculiar corrections and make this f function probably rather difficult. The other thing is, if we think about this f function, that it's what are we actually doing here? Stress, energy, momentum, and so those are all commuting operators, but they don't commute with position. And so um, essentially, to create this operator, we have to um, make perfect observations. So, in that sense, the uh, um, curvature tensor is actually the manifestation, the most real manifestation of the wave function. And so this is the kind of QM equals GR perspective. Kind of realized here because we're starting from the wave function and going to a gravitational field, but the question is, does that gravitational field what gravitational fields have a compatible wave function that would generate that manifold? Now, is there anything else to cover here? The boundary conditions are very interesting because if we're thinking about an S matrix, normally we're imagining things coming in and out from infinity, and that's a nice, and also there's essentially no notion of time because we're just looking at the probabilities of things coming in and out. Now, in this notion we can draw some kind of, using post-selection, some idea of, not if not trajectory, at least energy density. And and that is sufficient to give us relativity. Now, the point here is what's going on at infinity is this is slightly different from the S matrix we've been looking at, where time is compact. The notion of putting it at infinity is to try and have a situation where the field theory is non-interactive. So it's just a free field theory. And then as the particles come in the standard formulation of an S matrix, those evolve and then come out, but there's no notion of time, and there's just we don't have any idea of what this process means. Now, again, so we can see here there are some problems already reconciling this with effective field theory. Somehow the graviton, to get that is the effective field theory of gravity, and here it's just very, very complicated because as I said, we can be varying the metric here. So this is going to be just a more complicated manifold with more subtle solutions, and there are few things that might even be testable, which is quite interesting about this. For example, you can measure the field strength with post-selection to see whether the field strength is as expected. And so there do seem to be testable features. Of course, and the other thing is to do with time, and is this a direct delta? Now, there's suggestions that this is, if we're assuming, and there's no reason not to assume, effective field theory, then there's some very interesting kind of no-go theorems. One of which is that if we want a UV completion, then we're forced to either have a strongly interacting theory of gravity or have an infinite number of modes of gravity, so which is reminiscent of string theory. Now, in a situation where we have an infinite number of modes, that can only occur in an infinite dimensional space, in which case we would expect to have a Dirac delta function. So if there were only a finite number of modes, well, yeah, I don't really know. That's just something to look into. And so the other thing is, how does this model compare with Gerard de Hooft's model with CPS inverting black holes? Now, this is just very interesting because there are issues obviously with both theories, but let's look at one where, so in this is the model for an eternal black hole. In the 't Hooft geometry. Now, both of these geometries have that we're going to look at have the advantage over normal ways of doing it that there is no longer a problem with the information paradox, because let's say in 't Hooft's model we get a particle here, and then we have its entangled pair here being emitted, well, here backwards in time. It's very difficult to draw this because actually if this was the thing is actually going kind of like this, and then this is going backwards in time. So now, oh yeah, and we kind of have that and that, and these paths going back to here and all sorts of things. But the idea is that we can, there's not such a problem with the information paradox, because over the entire system, not all of which we can observe, the pure infalling pure states, pure in, is mixed between these two sectors. So overall the state is pure, but within this sector it's got a non-zero von Neumann entropy that keeps on going up. And so that's like the really puzzling thing about the black hole information paradox, yeah, is not so much what happens to the information, but how can pure quantum states go in and mixed states come out. So in this scenario, something has to happen to the negative energy particle, and in this model the negative energy particle goes into a sector that's able to take negative energy, and we can see that these two things, we want to basically align those 2 points. So this white hole here and this black hole there, these this singularity, we kind of want to make that singularity, so we got an identification here, and we got an identification here to here. So that what the thing about this is we can imagine this vertical particle as now being a virtual particle that is free for a while, but then eventually meets its partner at infinity. Now, but the thing about this model is what's happening inside the black hole. In Tvsf's model, we entirely cut out the black hole interior, and we're just left with an identification of the boundaries. Now, what's odd is it's a very reasonable solution, and very strangely, when I first started looking at this system, that's exactly the same solution that I found too. It's like, yeah, that's a really natural solution. And but there's a problem about the what's happening inside here, because we're essentially just cutting off a whole thing. And the idea that I was thinking, because first of all, in this system we've just got one black hole which is essentially projectively connected to itself. In the model that I have, it's a bit different. It's really hard to draw. I imagine it like this, where we have a number of black holes, let's say, that exist at certain times or in space, and then say we have the Big Bang here, or white hole here, and then we have its corresponding black hole event horizon there. But these are essentially the beginnings and ends of the universe. So we have some quantum field that then interferes with itself back here, giving us exactly the picture that we've got already, the traditional. But now we've got singularities here at all of these places. And so what we want to do is make any infalling particle here, the whole thing is in a cosmic loop. So there's a time delay from here to here, but then we want this thing to hang around in the interior. It's just a delay line long enough to mean that when time flows backwards, that Hawking particle is released at exactly the right time in the cosmic cycle. So that means that in this model, a black hole, let's call it, or white hole, is equal to CPT inversion. And in this one, we've got the CPT inversion to a different sector. And so here we got essentially our normal sector and the backward sector here. And now everything is synchronized. So rather like in a conformal flow where we have streamlines meeting at exactly the right point, that it's the same here. We've got a kind of conformal system. That means that from the point of view of this kind of overall view of both sectors, everything is synchronous. And so this is a CPT inversion to a different sector plus a delay line. So this is the extra component, or extra two components from this model. The overall model still looks very similar, and in both of them we can put an arbitrary, because we can never traverse this, we can put an arbitrary gauge transform as well on here, as well as a 180-degree shift. And now what is this gauge? Why do we need this gauge transform? This is all to do with quantum computing, because if we imagine that we take H phi, sorry, we have H phi, some quantum system, and we imagine not that what can we do with it? We just got H phi. We can't really do anything with it except to check, is it equal to lambda phi, an eigenfunction of it. Now, phi is either an eigenfunction of it or not. Yes, we say that we use the Born rule to find the lambda and the and phi, and then know this as the equivalent of a non-halting computation. And so the thing goes on for another iteration to try and find a phi, if you like. So it's easiest probably here to look on this simpler one. If we take something spin up, and then it goes over here, it's going to go spin down, but then when it goes back here, it's going to go spin up. So that means that we've got an eigenfunction, which means this thing isn't a cycle, it's just a virtual cycle. So we can only make, if we were to do this with QED, we find virtual particles only. And so this is a bit peculiar, because that means that we need higher degrees of symmetry. So, for example, if we have a red quark, we could map it to a blue quark. And then to a green. And this is a 3 cycle. So basically by putting a gluon gauge in here, gauge transformation, and this, I did see this earlier, but it really points it out now that it's not, it's actually is the SU3 structure that seems to be pushing us into this case, non-halting. Because now we put in a red here, it goes across to a blue, and then it comes out green here. So there's no eigenfunction. We need to run it around again to find an eigenfunction, but that again is not an eigenfunction. We've only got an eigenfunction of H3 phi equals lambda phi. So what that means is this is where it seemed to link in with the now proven Langlands, that in these cases where there is no solution to the eigenfunction equation, we actually land up with a cyclical universe which is not a virtual particle, it's eternal, because it keeps on cycling. So there's no, we can't regard it as the result of a computation. And so that means that things like this will have their own independent existence, essentially, via what is Gödel's theorem, because these are, in a quantum system, these are wave functions that, using the standard evaluation of a quantum wave function cannot be proved to halt. So they do correspond loosely to Gödel statements. Which was the whole idea of this, really, but in reverse. But we can see how previously I'd looked at it in terms of QED, but now it seems that it actually requires a bigger theory in order to actually work properly. But this does bring out the so something has basically swapped positrons for protons. Because if we didn't have, if this was just positrons, we're only gonna get virtual particles, but and essentially the result of a computation. But as soon as we have protons, we can form a proper a universe that we can prove never halts. And but it's a mystery as to exactly how this substitution takes place and why. It does. If we think of this point as being a primary vacuum decay, then the antimatter components are heading in that direction and the matter components are heading in that direction. And so it might be that this is just essentially fixed into the initial conditions, and the fact that we can only really create states in the system by pair decay. We can't just willy-nilly create a particle. We have to decay a pair. And so if we're just decaying pairs, and there has to be some very peculiar event horizon issues going in here. Now, so I think actually we can see that there are loose ends here, and quite a few of them. But what it does appear to do is give some handle into how we can use not just a weak value, but essentially the everything but the phase of the wave function to determine a curvature tensor. And now, actually, let me just, I think I've been talking over the wrong picture for a bit. Let me just select a new source. Yeah, so here we have the 't Hooft picture, right? And we can see the spin cycling round, spin up, spin down, spin up. So that gives us this case of here. Yes, we have an eigenfunction. In the case when we have a red quark, it goes blue and then green, and so we have no case here. And this picture is showing how we have our sector here, our positive sign sector here, and then a negative here, and how when things can be held at the singularity until they're released at exactly the right time so that the whole system is synchronous. And so that means that all the path lines eventually land up in essentially closed time-like loops, and all of these time-like loops eventually all meet at one of these singularities at exactly the same time. So a kind of conformal structure. Um, and then we see, yes, that according to this interpretation, QED creates virtual particles only, and that things with these threefold symmetry H3 phi equals lambda phi, which can't be picked up by a single by a quantum computer running this algorithm, correspond to Gödel statements within that system, i.e. Statements that can't be proved to hold within the system. So the and then that is exactly the feature that is used, the non-halting nature of it, to create what we would say is a real universe, but one that's not a virtual particle. And then, so here in this picture, the Hoof picture, we have a black hole is equivalent to CPT inversion, but on a single sector, like linked by an Einstein-Rosen bridge. But in here, we have CPT inversion to different sectors and a delay line to accommodate for the synchronicity of the entire system. And I think that just about wraps it up. Other than getting in and actually writing down the forms of every field for the Lagrangian. Now, I guess that is an interesting topic, because there are so many different forms. You know, you can start with a standard model, all sorts of different Lagrangians for this, but they all will be multiplied by reverse wave factors, in order to essentially make the system deterministic. But that brings it, you know, that gets into questions like Unruh radiation, and are we talking here? What about? Is this a dynamical universe in the sense that what are we to make of accelerating observers, and are they experiencing different histories? Because of an accelerating observer, for example, if we take a vacuum state for a Rindler vacuum, it's a different vacuum, and so one could say that it's in a completely different sector altogether, and indeed one that has less information on its horizon. So you know, the nice thing is by using these approximations and effective field theories, we can kind of zoom in and see whether these things make sense, because there are a lot of extra terms that seem to come in effective field theory. And but one thing that is quite interesting about this as well is that if we look at it, the so-called cosmological constant in this is just the difference between the ground state energies between two vacuums, and so we have a kind of positive energy vacuum, and we have a negative energy vacuum, and together, you know, this can be enormous, and this can be negative enormous too, and so we can land up with a difference that is very small. So difference very small. Now, this is having a very small difference, so a very tiny cosmological constant is quite handy in a way, because at a Planck scale, we can get regions of positive and negative curvature, where we kind of get a positively curved bit, say here, and then we get a negatively curved bit outside. And then on the boundary, we'll get a flat. Now, that flatness is a kind of useful space to do holography on. Even though it's a potentially dynamical thing, there's no back reaction on it. So we can use that as a kind of foundation to build solutions. And the other thing is because at a tiny scale we can have these regions of positive and negative curvature near the Planck scale. Supersymmetry doesn't work very well in positive curvature. The vacuum state is metastable, but it works perfectly well in negative curvature. And so what that means is that we can have very, very short scale supersymmetry. But once we're, this is kind of Planck scale. And so what this means is that it fits in with the view of asymptotic safety, that new physics only really kicks in at the Planck scale. And this is saying that, well, at the Planck scale, when the curvature becomes so uncertain, that you can start to get regions of negative curvature, then within those regions you can have supersymmetry. And this kind of is similar to ideas that are coming around nowadays with regards to supersymmetry as being an internal symmetry, rather like other gauge symmetries, and which is leading to some very interesting possibilities. And at a tiny scale, this kind of looks a bit like that anyway. It could be seen to be an internal symmetry, depending on how these neighborhoods are organized. But it's, and because curvature is an absolute thing in this, it is a relativistically well-defined thing. All of these, the flatness is well-defined. And so, but that, of course, doesn't say why isn't the Planck, why isn't the Higgs mass at the same scale? Why is the Higgs mass so light relative to this scale? And again, this is just all kind of conjectural and loose work at this situation, because it's just a lot of open questions really at this stage. For example, this is not really a string theory, but it's got kind of some stringy features to it, and it might fit in well with the string theory, and one reason is that if we have two sectors, it's possible to implement things like Feynman diagrams in a way that we actually have an extra string over here. So it's kind of like an interaction between two sectors where we get two things over here, say, going to one thing over there, a time reversed version of it, like that. And then we imagine these to be strings, and then we can see that actually the number of particles in this system is remaining constant. So it's possible by using these kinds of couplings to create a system with a finite number of particles, but from within one frame, it looks as though particles are being created and annihilated, but actually they're just being essentially permuted between the sectors. One moment we got one there, then two particles here go to two particles here, so two. It's quite fun. Now, how does this go? So, yeah, but basically you can see, right, at each stage, well, there are three particles here, but there are only 2 particles here and then 3 here, so we've got to have an extra particle state somewhere in between, unless it's 2, 3, 3. Anyway, I'll leave that for another thought, but it did appear to me, I'm potentially wrong, that by using a second sector we can actually organise it so that Feynman diagrams conserve the number of particles, but maybe that's nonsense. But hey, till the next time, and I'll see if anything else turns up that's interesting, but so far it does look like quite a few more things are working than expected, but obviously the difficulties are gravitons, finding out how to incorporate, well, we know how to incorporate them because we got the effective field theory, but you know, that is one thing that hasn't really been pushed through because it's considerably harder than the rest of it. But because it is nothing else is directly affecting the metric in the same way. But the gravitational particles are disturbing the background metric. So in a bizarre way, but the interesting thing is that the background metric, at least it's already been disturbed by the H. So all we really want to do is work out the gravitational terms in this H and then how to map it onto the energy density. So there's a lot of interesting work to do there, but it does seem like that it's a model that reduces to QED, and you know, it's an extension to QED in the sense that we're adding additional structure to it, but not much because it's all structure that is determined by post-selection. And that essentially, I think, wraps this up for the moment. Thank you very much for watching this, and look forward to any new work that I find later on. All the best.